Right. So in the last class, we have learned that if we have a wave function psi, which is a function of x and t, then it can be expressed as a the eigenfunctions and so on and so forth. And these eigenfunctions, since they are orthonormal, therefore they can be treated as the basis vectors. So the picture that we'll have in our mind is something like this. Can you see the presentation screen now?
Yes, sir.
Yes, sir.
Yeah. Okay. Let me delete this. Something is going wrong. It is no. Okay. Here is this and so all I said was that the psi function can be expressed as a linear combination of the energy eigenfunctions. And since the energy eigenfunctions are orthogonal vectors, naturally orthogonal functions, they can be treated like a system of orthogonal vectors. And you also have the psi function. Okay, so the psi function is like this. Sorry. And then you can imagine that this psi naught, this is okay. I'll put it the other side because I need to do it in the proper order. Psi naught, psi 1, psi 2, and so on and so forth. And obviously, there will be a much of such axes because this actually goes to infinity. But in order to aid our visual representation, we will often draw pictures like this, cartoon pictures. But I actually want you to have this mental construct that what we are dealing with are vectors like this. And vectors like this, we understood, that can be represented as a column vector comprising the components. The moment you specify this, the vector, the function is completely specified, and that will happen only when you have defined the basis. So only when you have defined the basis, you can express a function as a column vector, and that in the last class. You might have noticed that initially I was telling that the functions like this function are similar to the vectors. The functions or vectors behave similar to the behavior of the functions, in the sense that if you have a vector, if you have another vector, and then you can always obtain the projection, the projection like this. Projection here is nothing but the is nothing but the projection. So you see this operation between functions is similar to the operation between vectors, and the operation of the bracket is similar to obtaining a projection between vectors. So at some stage I was talking in terms of giving you the pictorial of treating functions as vectors, and at that stage somebody asked me, I recall somebody asked me, what is a conjugate of a vector? At that stage I said, wait, first you get the picture of a vector, what you learned in your first year as the character of vectors, and then at some stage will come. But now we have come to that stage. The point is that how do you obtain these numbers? These are obtained as the projection of the psi function on, sorry, this was psi 1. And this, since both of these can be complex numbers, these can be complex. And if these can be complex, then in order to construct something like this, bracket, you will have to do, you will have to produce a vector out of this column vector. So a ket, if that is represented by a column vector, a bra will be represented by a row vector. And not only that, in order to get the dot product correctly, you will have to get star. So I said that if you, let me erase this part and then I'll go, then it would be easier for me to work out. Yeah. Then I said that there is a vector V, sorry, here. If I have a vector V, which is summed over I, Vi, and the I kets. Essentially, I'm talking about something like this. Then it is actually like writing it as 1, V2, V3, and so on and so forth. And that will be same as V1. The first one is 1 and all zeros. The second one is, first one is 0, then 1, then 0, 0, and all that, and so on and so forth. And the nth one is all zeros, and here the nth position as 1. Okay. This is the picture that I wanted to give you, that now we have the whole function expressed as a column vector, which is actually a linear combination of this. These are also column vectors, these basis vectors. Okay. And these basis vectors denoting as I. Now, if you have A times a constant times this vector V, then effectively this is A, V1, V2, and so on and so forth, A, Vn, right? And now if you want to convert that into its equivalent bra, the bra will be a row vector, but the row vector will comprise the conjugated thing, and A is also a constant which can be a complex valued constant, so it also will have it also will have the stars. So it will be V1 star, A2 star, V2 star, A3 star, V3 star, and so on and so forth. AN star, VN star. This is essentially writing the bra as V, and here A, star. Okay. Let me get some spacious. So you with a constant multiplied to it can be converted to a bra, equivalent bra, with a constant multiplied to it. But in this case, in order to convert that, the A also has to be conjugated. Now, since Vi, all this Vi, is nothing but the projection of V onto the ith unit vector, basis vector. Therefore, okay, no. And your Vi star, the conjugation of that can be obtained by just reversing the positions. We have already learned that. So this is V. Okay. So, and your V, this is something that we learned in the last class. V is I over the projection operators with phi. Okay. And this whole thing, each one is a projection onto the ith basis vector, and the whole thing put together is the identity operator. Okay. Now its adjoint will be, that means its bra will be phi. It will be summed over I. We have already seen this, so it is V I and I. So we have learned how to convert the kets, which are column vectors, into the bras, which are row vectors. All right. Now, here we have taken a particular set of basis vectors. But the basis vectors, what we take as basis, is not given. You choose them. And accordingly, these will change. Okay. So depending on what you choose as the basis, your components will change. And that is something that we'll have to deal with much detail later. But one is to understand that the numbers C1, C2, and everything actually choose as the basis vectors. Okay, good. So we have understood so far that kets are column vectors. Sorry. And bras are row vectors. Good. So I have a column vector in our mind's eye. We will imagine a set like this, and I have a vector like that. Now, I want to know the operation of an operator. So an operator. Here I can always get the projections. Get the projections, and those projections will tell us what are the values of the coefficients. That's fine. But now I have a vector and I operate on it by an operator. what should the operator be? Obviously, a vector like this being transformed by an operator into another vector. So this is of an operator. And that you have learned from the first year, what the A must be, it must be a matrix. Okay, so operator must be a matrix. So we have to find out what the character of that matrix will be. But we have at least, it's easy to understand that something that transforms a vector into another vector is a matrix. But one thing is clear. If we know the action of the operator on vectors, then we know the action of the operator on any vector. Why? Suppose there is a operator omega operating on the basis vector I to give another vector I prime, then operating that same operator on any vector V will give you omega. Now I will decompose this into the components. These are Vi, I, summed over. This is nothing but summed over I is a number, so that remains. The omega becomes operates on the I, so omega operating on the I vector, which is nothing but I Vi prime. So that's what we have obtained, right? So it essentially means that if we know the action of an operator on the basis vector, we also know the action of the operator on any vector in that space. Great. So on that basis, let us proceed. Given any basis, how do we define the operator as a matrix? That is a problem we are facing now. Suppose the function psi is obtained as an operator A operating on another function phi. This function is a column vector, this function is a column vector, this function is a matrix, square matrix. So we have to find out what this matrix task. So this is in terms of the basis. This is important that we have already defined the basis, and in that basis we are trying to define this. And if you have defined the basis, then we can define the psi in that basis as some j is equal to 1 to n c j, the basis I say u, the basis is u. Okay, that means u1, u2, another writing badly. So this is u j, where your Cj is nothing but uj psi, and our phi is also defined in a similar way. Now it will be j is equal to 1 to n. You have, I'll say aj again, where aj are the projections of the phi on the uj. All right. Now we had this, and we had each of these into their components, so we can substitute this here. So if you substitute this here, we get j is equal to 1 to n cj, this is uj, we have written the psi part, is equal to a operating on this. It is j is equal to 1 to n. This is aj uj. These ages are numbers, so the operator actually operates on these gets. So we can write this as 1 to n. It is a operator uj and then aj. Now let us operate ui draw from the left. If you put ui bra from the left, then what you have is that this is not affected by that, is affected. So you can write it as sigma j is equal to 1 to n. It is cj, then ui uj. Okay. Now here we have, okay, what is this? This is nothing but delta ij, cj. So that will cancel off everything where I is not equal to j. So this is nothing but ci. Everything else cancels off. Is equal to have j is equal to 1 to n. I have this and I'm operating here. So it is ui a uj, and here I have a. Okay. This is, I can say that this is j is equal to 1 to n. Let us call this whole thing as aij, where aij is nothing but this. Notice what is happening. We had one vector phi on which a was operating to give me psi. Phi was completely given in terms of the vector a, that means a column vector with a's as the elements, to give the column vector with c's as the elements, and we can see that the ci's are given as this, which essentially shows that these are the matrix elements. So matrix, the A operator then is a matrix. Oh, sorry. I'll kill it and do it again. Is where the first element is U1, A, U1. Second element is U1 operator operating on U2. You have at the end U1 A operating on UN. Here it is U2 A U1 ultimately you have UN A U1, and here at the end you have UN A. So effectively the operator is given by a square matrix where the elements is the element here. A operating on U2 is the basis vector, second basis vector. Whatever you get, you bracket it with U1, whatever you get, that goes here, and so on and so forth. That fills the matrix. And ultimately, you have a situation where vector, C1, C2, Cn is obtained as this matrix here. I will write it in this form: A11, A12, A1, sorry, A1n, this has to be capital. AN1, A. Now you understand what ANN is this one, and multiplying A1, A2. So the whole thing becomes a simple matrix equation. And this is something you are accustomed with. You know how to manipulate them, you work with matrices. So the whole thing becomes simple, much simpler to handle. So far you are using functions and how the function evolves that you are obtaining in terms of a partial differential equation, which is sometimes difficult to solve. But now we have expressed in terms of the vectors. And you will soon see the advantages of that. But before that, let us work out a few things. Let me delete this thing. If there is a question, you ask, because I'm going to delete this.
Sir, could you please switch off your video, because sometimes your voice is breaking. So if you switch off your video, your voice will get more bandwidth, so there will be no problems.
Let me try. Is it okay now? Is it better?
Yes, sir.
I'll switch on my video. Now we can start. We know that the matrices, the operators that we deal with in quantum mechanics, they are hard. We have already learned that they must have the character that their expectation value should be a real number. Their eigenvalues, that are the values that we can actually observe, they must be real numbers. And for that, we had concluded that every operator that we deal with must be Hermitian. So the conclusion is that A must be Hermitian. So what will be the demand on the elements of Aij? Aij. This is what we are investigating. What should be the demand on the elements Aij if these are to be Hermitian? And Aij, as we have just seen, are obtained as U1, Ui, A, the ijth element. Now, since A is Hermitian, Therefore, presently it is operating on the right hand side, and we can now bring it to the left hand side. So because of the Hermitian property, so we can write it as A U I. This vertical line is not necessary. A operating on UI UJ. This is nothing but I can bring the uj to this side and this thing here. If you do that, if you interchange the position of the ket and the bra, you goes with a star. So we can write this as equal to uj a ui star. So I have interchanged the positions, and if you interchange the position, it gets conjugated. We have already learned that. Now, since again, I can now write this as in the familiar form, uj a ui star. Notice that this is the ajith element. So, what are the conclusions? Conclusion number 1 is equal to j, the diagonal elements. Conclusion number 1 is it must be real. And 2, the off elements what was the character of the off diagonal elements? I complex conjugates. Operator A. Okay, so the UI are the eigenfunctions of the Hermitian operator A. Then Aij, that's what we are trying to figure out, is UI A Uj. Now AI is operating on its function. So this will be nothing but the eigenvalue times the eigenfunction. So we can get the eigenvalue out, which is a number. So it is Aj Ui Uj, which is nothing but Aj delta. Okay. So what does it mean? It means that it will exist only when I equal to j, which means only the diagonal elements will exist. Everything else will be 0. And the diagonal elements will be the eigenvalues. Okay. So if this condition is true, that means the basis vectors to be the eigenfunctions of the operator that we are trying to define as a matrix, then it will be A will be a matrix with all zeros. So all these are A1, A2. These are the eigenvalues. All right. On this, if you have any question, and then we'll look at how does the Schrodinger equation look in terms of vectors and matrices. How does the Schrodinger equation look in terms of vectors and matrices? You are exposed to the Schrodinger equation in this form: IH cross del t of psi xt, talking in 3 dimensions r and t. This is something that you need to write that, is equal to h as an operator operating on psi r. This is the expression of the Schrodinger equation you are used to, you know. And we know that psi is now psi r and t is now expressed as, in terms of the basis, since it depends on t, this will also depend on t. Okay. In this basis, I am not at the moment specifying, but you know that it can be expressed in the energy basis, where the energy eigenfunctions can act as the basis vectors. So this, we can substitute it to get IH cross. It will be del t of j is equal to 1 to n. This is Cj t uj of r is equal to h operator operating on the same thing, sum over j Cj t uj r. Okay. Before proceeding, I would like to express this in terms of the kets. So this is nothing but IH cross del t j is equal to 1 to n, Cj is a, but here this is the ket, and in the ket we don't write what is function of, so I have to write that way. Cj t ket. Now we operate from the left. From the left with ui, sorry, with the bra ui, then we get IH cross del t here. This will remain as it j is equal to 1 to n Cj t, and this becomes ui uj, and the right hand side becomes the h will go to this side. It is j Cj t and this one is ui coming to from the left, h operating on uj, h operating on uj. Okay. Great. This is IH cross del t of what? You notice that this goes to 0 unless I is equal to j, and therefore this is nothing but ci as a function of t. And in the right side, have this is nothing but H as a matrix, H, I, J, the ijth element of the matrix H, right? So I can see that what we ultimately get is over J, H, I, J, C, J. This is function of T. So you notice that you started with a differential equation involving functions. Now you have arrived at a involving these coefficients. How do the coefficients vary? How do the vector elements vary with time? And you can see that the way the vector elements vary with time is related to, in the right hand side, you have the Hij matrix, the Hamiltonian matrix, times the Cj. So it is actually like, if you write each line, the C1, sorry, I'll write that in space. C1 is equal to H, sorry, H11 C1 plus H12 C2 plus H1 N, like that. And then like C2 is similar, Cn. So you see this becomes, sorry, see, this is I H cross del del T. C1 or is this? So it is a differential equations. It's a differential equation, and these elements have to be found by this method, by looking at what we are choosing as the basis. If we choose the energy basis, then by the theorem that I just proved, this becomes a diagonal matrix with the energy eigenvalues as the diagonal elements. So it becomes a very easy equation to write. But if you use other bases, then it can be more complicated stuff. But nevertheless, what we have achieved is to reduce a partial differential equation involving functions into equations involving the coefficients. And that is much easier to solve. Okay. 5 minutes left, so let us stop here, and if you have any questions, you ask, and then we'll in the next class we'll go on to further discussion on this. Do you have any question? Yes,
Sir, I have one
Sure.
question. Sir, at last, so we obtained that the Hamiltonian matrix will just contain the diagonal elements, just like the proof you have done.
Yes,
Okay.
provided you choose the basis of the energy eigenfunctions,
Okay.
then only it becomes a very simple diagonal matrix with the eigenvalues, energy eigenvalues as the diagonal elements. Yes.
Sir,
What is the question now?
in the last step,
Yes.
when we are representing that inner product, the H operator, which we call the Hij elements that we wrote, so they would also fetch a constant, right? So that should also come in the last.
Wait. Which step you are talking about?
Sir, the second last step,
Here.
the inner product that you represented by Hij.
Yeah.
So that should So the H operating on Uj should also bring out some constant Aj, right? So there should be one Aj constant also.
No, wait. Here, we have not yet written what this whole thing is. What you have done is essentially H comes here, stays here, and then this is operating from the left, thus giving this. Now, what you obtain by actually evaluating this is a secondary matter on what you choose as your uj. Now, provided you choose the energy eigenfunctions as the basis, then H operating on uj will give the energy eigenvalue, and then yes, it will come out. But only in that case. You get the point?
Sir, the choice of basis is not yet clear to me. The notion that you are choosing energy eigen basis,
Yeah,
I'm not able to get that.
Okay, we know that in the harmonic oscillator there is the energy eigen functions. Something are there, right? These are this one would be a Gaussian function, this will be x times the Gaussian function, this will be x squared times Gaussian function, so on and so forth. But all that we know is that the property is that psi n psi m is delta ij, it's delta mn, which means that they are orthonormal vectors, and therefore these can be taken as mutually orthogonal basis vectors. So if you choose this as the basis vector, then your H matrix will comprise only the diagonal elements, and these diagonal elements will be the eigenvalues. That means the first diagonal element will be the ground state eigenvalue. This will be the first extra state eigenvalue. But this is not the only choice of the basis that you can have. Like if you have a vector, you can express that in a basis like this. You can express that also in a basis like that. Right? Nothing stops you from either expressing it in this basis or in this one, or in this basis. Both are right. All I'm saying is that this choice of the basis is not a unique choice. You don't always have to do this choice. And for different purposes, you might actually choose different bases depending on your purpose. But provided you choose this, then this becomes simpler. It becomes just a constant times uj, and therefore it becomes a constant times delta ij. That's true. Is the point clear? What other choices of the basis you can have, that I'll come to later. At the present moment, I am not answering that question. I'll come to that later.
So, sir, when you decompose psi as summation j equal 1 to n cjt into ujr, so you are essentially taking the uj's as the basis or the cj's as the basis?
No, uj's are the basis. Cj's are the projection. Cj's are the projection of the psi. So if this had been your psi and this had been your uj, then this is cj. Is that clear?
So you are also multiplying the time dependent part, the e power minus iet by h cross with that projection, and writing that whole thing as the cj.
You can say yes. Yes. That's why it depends on time.
Oh, okay, sir.
That's why it depends on time. Any other question? No, otherwise it's already time today. We'll come back to the next class.